Camera is here. You need to come here.
Oh, I did too.
Yeah.
The title is Approximation of Fixed Point of Monotone Asymptotic Non-Expansive Mapping, or Asymptotically Non-Expansive Mapping. The talk is quite long, I'll be honest with you, so I'm not sure I will get to the end, but if I am, that will be amazing, okay? So I will go a little bit fast on the introduction, which explains a little bit the usefulness of fixed point theory and its applications to different areas of science, from differential equations, topology economics, and game theory, dynamical systems, economics, etc., etc. So I will not dwell too much on this, okay? I will start with the Banach contraction principle because it was the Banach contraction principle that started the idea of monotone mappings. Okay, so I want to go from there. Okay, so the Banach contraction principle, the statement is quite simple. Okay, and it involves, it's an old theorem that has been known for many years. It involves Lipschitz mapping. Okay. Where you see the definition in front of you, and metric space. Okay, so the theorem is stated as follow. You have a contraction, so the Lipschitz mapping is less than 1, and what happened is that the iteration is a Cauchy sequence, and it converges for any point. If it iterates, it converges
Recording stopped.
To a fixed point, and the fixed point omega can be approximated by the iteration Tn of x. Okay, so there is this kind of numerical approximation that you can use. Okay, now once we are done with k less than 1, a contraction which was known for many years,
recording started.
It's natural to ask what happened for k equal 1, which is the case of non-expansive mappings. Okay, so the people asked, can we go a little bit more than k less than 1? Okay, and if you go to k equal 1, in other words, you have here the which is a metric space, a non-expansive map. We call them inexpansive when k is equal to 1. Does it have a fixed point? And the answer is obviously no. They found it right away. Okay, and the example is, for example, here you can take the unit circle, okay, in the plane, and you take rotation with a small angle, and you see that it is an isometry, but it fails to have fixed point, right? But if you look at the isometry over the entire plane, okay, it has a fixed point. That's the origin, okay? So what is the origin? It lies inside the unit circle, okay? So people thought, oh, maybe we can capture the origin by adding some kind of convexity on the set, okay? Keep in mind, I put convexity here between quotation mark. Why? Because I was dealing with the metric space, okay? So we need to be careful about what do we mean by a convex metric space. That's another discussion that I will not be talking about here, okay? So they thought that was the case if we add convexity, okay? Just linear convexity to make it easy on us. And by the way, that's what they assumed anyway. So here you have a convex closed bounded subset C of a Banach space, and you have a non-expansive map. Does it have fixed points? And the answer is no. Okay? So here is an example where you have a convex of functions, positive functions, continuous between defined on 0, 1, and with such that f of 1 is equal to 1, and you take this map t of f of t is equal to t times f of t, okay, and t is non-expansive, and it fails to have fixed point. I'm not gonna go in details, but it fails to have fixed point. It doesn't have any fixed point. So what's missing here? What's missing is maybe some kind of compactness is missing. Okay, good. Wojtek just joined us. Kozlowski just joined us. Welcome, and you didn't miss much. I'm just at the beginning. Okay. So as I said, if you take the case of a convex set, we know that it's not enough. I mean, you may have a non-expansive mapping on a convex set, and it still fails to have a fixed point. Now, what's missing? What's missing is some kind of compactness. I left it like this, okay? Some kind of compactness or topological property to be added on C, on the convex set, on the domain, okay? To be able to have something. And by the way, I wanted to see how I'm going piece by piece over the history to bring you to what we are doing in the recent years, okay? So we know that it fails. Non-expansive map may not have fixed points in the convex sets, closed convex. But now let me show you something interesting, okay? That if you take a closed convex subset of a Banach space and you take a non-expansive map, you can epsilon perturb it in a convex combination, and you are able to generate a point as close as you want to be a fixed point. So look at the bottom. So of course it's an application of what? Of the Banach contraction principle, okay? And you have this little calculation, and it gives you this point x epsilon, such that the norm of x epsilon minus t of x epsilon is less than epsilon diameter of C, if C is bounded, of course, okay? If C is bounded, then I can get them as close as I want to be a fixed point. So we may not have a fixed point, okay? A non-expansive map may not have a fixed point, but it has something called approximate fixed point. So we are almost a fixed point, okay? Great. So now nothing was done. This was known. I mean, what I said before, it was known. So nothing was done for almost, I would say, 35 years to 40 years till 1965. Amazing. 1965, something happened. We don't know what it is, but something really major happened, okay? Which is that we had three, I mean, to be honest with you, three mathematicians, Browder, Good, and Kirk, who published 4 papers. Okay, not 3. You will see them here, just 3, but in fact, there were 4 papers. The first one, which is paper by Browder, the result was not done in uniformly convex Banach spaces. Okay, the one I'm putting reference here at the bottom is the one that was published with the uniformly convex Banach spaces. But in fact, the first one was done in Hilbert spaces by Browder. Okay, then Good published his paper in uniformly convex Banach spaces, and then of course Browder went back to revise his proof, his original proof, to show in fact that the idea he used is valid also in uniformly convex Banach spaces. That's what I meant by this. Okay, so this is what they proved, both of them. They proved that if you have what? A bounded closed convex set of uniformly convex Banach space, and if you have a T which is a non-expansive map, then T has a fixed point, and the set of fixed point is closed and convex. Okay? Great. The technique by both of them is different. Some of you will say, oh, okay, so maybe this guy picked from this guy, or this guy took from this guy. But the technique, how they approached it, is slightly different, okay? Slightly. One uses what we call the dummy closeness principle, while the other one uses the issue of, the concept of asymptotic center, okay? Note that in this case, if you are uniformly convex, you are reflexive, and in this case, you have the weak compactness. Remember what I told you earlier. We may need some kind of compactness, okay? Now, the third theorem was done by the third, I'm sorry, not the third theorem, but the third major breakthrough was done by the third mathematician that I talked about him so many times. His name is Kirk. So he proved what? That if you have, and that was a totally different approach, totally, and by pure accident, okay? So Kirk proved that if you have a property known as normal structure property, okay, then again, with weak compactness, you have what? A fixed point, okay? What does it mean to be to have normal structure property? It means that the smallest ball you can find for any convex, you can find a point inside the convex, and you can find such that the radius of the smallest ball which contains the convex is smaller than the diameter, okay? So that's what it means. Okay. So it's a property that Kirk found by accident in a paper written in Russian by two mathematicians, Brodsky and Millman, and they were proving something about invariance point by isometries defined on a convex set. And they used this property, and he was looking at the geometry of that paper, not the fixed point. No, by no means. He was not a fixed point mathematician anyway. So that's how he came up by accident to find this theorem. Now, what happened? Uniformly convex. Keep in mind, I started with the Banach contraction principle 1922. I went to 1965 with the main theorems of Browder-Good and Kirk, and exactly what happened. And here in this case, uniformly convex Banach spaces, they have normal structure property. Therefore, the theorem by Kirk is more powerful than the two theorems of Browder and Good. Okay? But keep in mind that the Browder and Good fixed point theorem, okay, are constructive. They are using a property of the uniformly convex spaces, uniformly convex Banach spaces. While Kirk is a proof that uses the Zorn lemma, because he goes to the minimal invariant convex set, and then he shows that it's a single point, and that's how he shows that it is a fixed point. So the approach is slightly different. Okay, the first two are constructive, while Kirk is more about set theory and kind of non-constructive, because a student of Kirk, a Turkish mathematician, worked on this issue of constructive versus non-constructive. I don't want to go into this discussion. Now, the following years, almost 20 years, almost 15, 20 years, okay, that followed this 1965, saw a lot of people working on the normal structure property, okay, and that was the whole discussion was about normal structure property and the geometry of the Banach spaces for which you have the normal structure property, for example, what we call uniformly convex in every direction, etc., etc. I'm passing by, okay? So here, the next, at the same time, oh, I forgot to mention, here I didn't put a slide, that there was a paper right after that was published by Opel, where he noticed that Hilbert spaces and little LP spaces, they enjoy a certain property that I will be talking about later on, for which it gives him also what? A fixed point, okay? Using the ideas of Browder and Good. So using the ideas of Browder and Good, he was able to prove the existence of fixed point, okay? But in a class of Banach spaces which is weaker than uniformly convex, okay? Next, we have hi Butaina, welcome. The people started asking, we have k equal 1, what happened now if k is bigger than 1? Now this is interesting, okay? So, k less than 1, contraction, Banach contraction principle. K equal 1, that's non-expansive. So what happened if k is bigger than 1? Okay, and for k bigger than 1, what we call expansive mappings. Okay, what are the challenges when you do k bigger than 1 compared to the previous cases, k less than 1 or k equal to 1? For k bigger than 1, there is a chance that the iteration will explode. Okay, because the distance they start to increase, right? And then people said, okay, fine, let us now control this business by assuming that the domain is bounded. So you are defined on a bounded domain, it's a self-mapping, so you don't have a problem with the iteration exploding. Okay, so do we have fixed point? Two directions were at that time considered, under this problem of expansive mappings, two directions. One is known as the asymptotically non-expansive mapping. Okay, and the second one is what we call uniformly bounded Lipschitzian mappings. Of course, there were some slight changes. I'm talking about the big lines, okay, that developed the whole theory. I'm not talking about here about some variants here and there. Okay, I'm talking about the attention of all the people working, the whole group, okay, worldwide, of the people working in fixed point theory, these are the directions that they were following for the last 35 years almost. Okay, so there's two directions. Let us start with the second one. I want to start the case of uniformly bounded Lipschitzian mappings. What does that mean? It means that the Lipschitz condition, okay, all of them, they are bounded. The Lipschitz constant are bounded. Keep in mind, it's bigger than 1, so it may tend to increase the Lipschitz constant, right? So this is what's going to happen if k is bigger than 1, okay? Because easily you have what? That the Lipschitz of Tn is going to be k to the power n, and since k is bigger than 1, it's going to explode. No, we take the class where the Lipschitz constants are uniformly bounded, okay? So do we have a fixed point, okay? And what's amazing is, this was noticed right away, that if you give me a uniformly bounded Lipschitzian mapping, I can find an equivalent distance. I didn't say the norm, okay, because this is Banach. I can find an equivalent distance for which T is non-expansive. And you have the definition right there, right? Good. So now, do I have a fixed point for this distance, okay? Which brings me to, I don't want to go in details about this issue, but it brings me to a beautiful problem, which is, given a Hilbert space, okay, let's say little L2, and we know that if you take a non-expansive map defined on a bounded closed convex subset, it has a fixed point. That was Good, that was Browder, that was Kirk, all of them. Yes? Hilbert. Now, what happens if I take an equivalent norm? Guess what? This problem is amazingly still open for more than 50 years. Now, let's go to the case of asymptotic non-expansive mapping. I didn't want to tell you some beautiful results of Bayon, for example, that they have a counterexample where it's uniformly Lipschitzian mapping, but it fails to have fixed points, and also some beautiful positive result that, okay, if k is a little bit bigger than 1, but not too far, in the case of uniformly convex Banach spaces, or if you have the Lipschitz constant bigger than 1. I don't want to go into all this, okay? But because the focus here is not on uniformly Lipschitzian mapping. The focus here is on asymptotic non-expansive mapping, okay? So what does it mean, asymptotic non-expansive mapping? It means that you have the iterates that are Lipschitzian. Pay attention here. Huh? The iterates are Lipschitzian Lipschitzian mappings with the constant Kn. And to be asymptotic non-expansive mapping, it means the limit of the Kns is equal to 1. In other words, the iterations are almost becoming non-expansive. The iterations are almost becoming non-expansive. Okay? That's what it means. Okay? So, when this was done, it was in the 70s. Okay, I want to tell you something very, very important, because I was, a baby at that time dealing with this business, so I learned some stuff, but the people before me, Kirk, Goebbels, etc., they did not know about this. Okay, that was the French school. The idea here is, if you have a Banach space, okay, there is a way to build a bigger space, okay, what we call the ultra power of the Banach space, okay? And what's amazing is, if you have a mapping which is asymptotically non-expansive, in a natural way, you can find a map in that ultra power that is non-expansive. So it captures that asymptotic behavior, okay? And from there, it makes a lot of proofs somehow easier and nicer to understand. Okay, but it's very hard to deal with what? With the ultra power. It's very hard to deal with it. For example, just to give you an idea, okay, if you take an asymptotic non-expansive mapping in the case of a hyperconvex space, we don't know if it has a fixed point till today. But what I was able to do, if you go to the ultra power of the hyperconvex space, okay, I can show that it has almost fixed point. Okay, almost fixed point. I was not able to prove the existence of fixed point. Why? Because we don't know, in fact, I'm sorry, we don't know under what conditions the ultra power of a hyperconvex is hyperconvex. So just to show you that approach is very complicated. In any case, who introduced this concept? This concept was introduced by Goebel and Kirk in 1971, published in 1972. They came up with this, and they published a paper where they proved, in fact, that such mapping, I believe I put it somewhere, here we are, that such mapping has a fixed point if the space is uniformly convex and the set of fixed point is closed and convex. In other words, similar to the case of monotone mappings. Similar. Now, Goebel said, recently I heard about it from a friend of mine in Spain, Thomas, he said that Goebel never understood why people are working in this area. They did it as a kind of bizarre class of mappings, okay? What's amazing is that a paper by Shu, I will be talking a lot about it, German mathematician, was published in the bulletin of the Australian Mathematical Society, okay, in 1991. And this paper, I just checked about 20 minutes ago because I saw it about a month ago or two, but I wanted to check it before I came online. And 20 minutes ago, I went to the bulletin of the Australian Mathematical Society, and they found on the front page that the most cited paper in the history of that journal is this paper by Shu on weak and strong convergence of sequences related to asymptotic non-expansive mapping. It's really amazing, truly amazing. Okay? In any case, now, how did Goebel and Kirk prove this theorem? Okay? So the way they did it, and I had to go back to their original paper this afternoon, okay? And it's written there that the approach is based on the original proof of Browder of 1965. What was amazing is that they did not use, Goebel and Kirk did not use the approach of whom? Of Kirk, because they don't know how to do it. We don't know, in fact, till today, whether asymptotic non-expansive mappings, they have a fixed point if you assume normal structure property. In other words, under the Kirk's assumption, we don't know if we have a fixed point till today. Now, I want to talk about Shu, okay, the one I was mentioning right now. So what did Shu do? He wanted to approximate the fixed point for such mappings, okay? He was doing some kind of iterative scheme to approximate based on Mann, Ishikawa, Krasnodębski, etc., etc. But what's new here with Shu is that he wanted to capture the non-expansiveness or almost non-expansiveness of the iterates of T. So his originality is in adding this power. In other words, he took the iterates, the nth iterate of T, and then he combined it with Mann, okay, and he came up with this iteration, and he proved something really beautiful, okay, some beautiful behavior of this sequence, whether it's weak convergence or strong convergence to the fixed point of T. Of course, very important that here Shu uses the fact that T has a fixed point. In other words, he does have a fixed point. This is very important, okay? And also he assumes something about the KNs, okay? That gives him some kind of regularity. It's not like any asymptotic non-expansive mapping, okay? It's a beautiful paper. I really love and enjoy this paper, okay? Next. So now, what is the question now? What's the title of my talk? The title is about monotone asymptotic non-expansive mapping. Okay, so the issue is about monotonicity. Okay, what I was giving you now is just a quick history from 1922 all the way to late 70s, early 80s about what? I mean, almost to 1991. About what? About classical asymptotic non-expansive mapping and non-expansive maps and the Lipschitzian maps, etc., etc. What is this business about monotone? Okay, so here, monotone, okay, some of you will wonder. First of all, I will show you two nice books, but in the meantime, let me start to show you what is the motivation. How did we start to get interested into monotone Lipschitzian mappings, okay? How? When I'm going to show you this, some of you may argue, wait a minute, they are not the original people. Huh? The original one is a Romanian mathematician, okay, Turinisi, who did this many, many years ago, okay? And I agree. I mean, I confirmed that. But here, what I'm talking about is, sorry, is the problem as this was discussed and discovered by Ran, Sayed, and Rörings. Okay, Rörings is a student of Ran, and Sayed was doing his he did his PhD in Eastern Europe, and he went to work with Ran in Holland. Rörings came as a student. She was a student of Ran. She did her PhD with him. So I mean, we know it as Ran and Rörings, but in fact, to be honest with you, you have to go back to the paper of Sayed and Ran in 2002. Okay, the paper by Ran and Rörings was published in 2004. In any case, the issue was under what conditions this equation has a solution. Okay, and what was amazing, without going to details, is that they discovered that if you look at the right-hand side of your equation, is like an operator or a map of x. Okay, so this equation is a fixed point problem. Okay, you have this transformation at x is equal to x, so you can use some kind of fixed point theorem, right? But what they discovered is that this map to the right, all this to the right, okay, is either monotone increasing in case of plus, monotone decreasing in the case of minus. But what happened is if x and y are comparable, okay, then this operator that you have here is a contraction, okay, for a certain distance, equivalent distance, equivalent norm to be precise. Okay, that's how the spirit of what they were doing, without going into details here about what they did. Okay, but so they came up with the following. So here, what do we have? We have a metric space. The setting is a metric space. Again, keep in mind, it was linear. Everything that they were doing is linear with norms. But because it is a contraction, okay, you can easily now state it in terms of a metric space. You don't need the linearity of the distance or the space, okay, in other words, to be a norm. So here you have a metric space, you have a partial order, because I told you if x is comparable to y, then that transformation was a contraction. And now what do? You say that t is monotone. In fact, to be honest with you, I'm borrowing the people working in artificial intelligence. That's what they say, or logic programming. But I mean, as mathematician, we should say monotone increasing, monotone decreasing, okay? If it preserves the order, okay? T is said to be monotone Lipschitzian if T satisfies the Lipschitz condition, but only on comparable elements, okay? Such mapping can be extremely bad, okay? We learned in analysis that Lipschitzian mappings are very nice. Like, for example, that they are uniformly, continuous, etc., etc., okay? Some beautiful properties. In the case of I'm dealing with here, in this case, it can be very bad, okay? Because we only have some kind of regularity on the comparable what? Elements, okay? Then you say it is a contraction, monotone contraction, if the Lipschitz constant k is less than 1, and non-expansive if k is equal to 1, etc., etc. I mean, here, of course, I will be dealing a lot with what we call an approximate fixed point sequence, okay? If I mention it, I will need it. It means just that xn and t of xn are getting closer to 0, as close as you want, okay? Now, look at the title, Banach contraction principle in partially ordered metric spaces. That is what Ran and Röhrings and the Sayed discovered. That's exactly what they discovered. Okay, so if you take T, okay, which is a contraction, and you take, or monotone, monotone contraction, you take x0, which is comparable to T of x0. Then if you take the orbit of x0, you will get a monotone sequence, okay, either increasing or decreasing, okay. That's what I'm saying here. And now using the contraction, monotone contraction, then you have this kind of what? Inequality there, which tells you, which can imply that Tn of x0 is Cauchy. Okay, so if it is Cauchy and they assume that the metric space is complete, then it converges. So now you have an orbit or an iteration sequence which converge. Don't jump and say that we achieved at the limit a fixed point. That's not true. It may not be the case. We can come up with some counterexample, okay? In any case, when the limit is a fixed point, this is the point. When the limit is a fixed point, these are some of the assumptions that you can put in. The first two, okay, they are Ran and Röhrings, but the last two, these two, xn increasing converge to x, xn decreasing converges to x, and you have these properties. They are due to Nieto and Rodriguez, okay? They discovered this. They improved on Ran and Röhring's fixed point theorem that was published. So you have a fixed point in this case, okay? It's not unique. You can approximate it even, but it's not unique. You can only do it from x, which is what you start with an x0, and you start iterating if the x0 is comparable to the omega, or to T of x0, and comparable to omega. It's very important to be comparable to omega. Otherwise, you may have more than one fixed point. Okay, Jarzynski did discuss this issue of what can you say about the structure of the set of fixed point. Okay, I don't want to go into this problem. Okay, now what happened to monotone non-expansive mapping? So we said monotone contraction, but what happened if k is equal to 1? Monotone non-expansive mapping. Okay, so what we did, we approached it like it happened before. We had to go, not stay in metric space, but to go to a Banach space. This is just, we built it the same way as I told you before. Okay, so here I went to a Banach space. We took, we're assuming that we have a partial order. I have a map defined on a domain C. I mean, you assume the good things like convex, bounded, non-empty, like before, okay? And what happened is we wanted to iterate T at certain point x0 that is comparable to T of x0. Because if you start with an x0 that is not comparable to T of x0, the iteration or anything you can generate from it is so bad, because T is only good on comparable elements. Okay, so what we did here, the smart way to approach a fixed point for T in this case was to look at what the iterations that we learned in the case of non-expansive mappings. So of course we are talking about Mann, we are talking about Krasnodębski, Ishikawa, etc., etc. So that's what we were trying to do. The same here. Okay, so you have Mann iterations, which is the extension of Krasnodębski as well, etc. And we looked at this sequence and we proved, in fact, so if you have x0 comparable to T of x0, then the sequence generated by Mann, okay, will be increasing if x0 is less than T of x0, and decreasing if x0 is bigger than T of x0. Okay, so you have this kind of behavior. Okay, and now if you add in some kind of, let's say, so here we are. So this is very important. So what we found is, with minimal assumption, we generated an approximate fixed point sequence. So in terms of what? In terms of numerical approximation, then you're almost there. You almost have a fixed point. But since, of course, in my area of research is there a fixed point? Not an approximate fixed point sequence, but is there a fixed point for such mappings? Okay, so in this case, as it was done in the general case, we needed to assume something And one of the first assumptions is what? That we were able to do it. The first that we were able to prove the existence of fixed point was with Opel condition. Okay, so if we have a closed convex monotone expansive mapping, comparable xn, we have this, yes. If you add now Opel condition, okay, that was discovered by Opel, weak Opel condition, okay. So here, this Opel condition, I wish I had a little bit of time to tell you about delta convergence and weak convergence in the case of hyperbolic metric spaces, okay. This is the key when we say the delta convergence in hyperbolic metric spaces and weak convergence are the same. This is the key. If you have Opel, then it's true. If you don't have Opel, that's false. Okay? So in any case, so here you have this beautiful inequality there, okay, that you see, definition of Opel, and the classical spaces that have Opel that was discussed by, discovered by Opel himself were Hilbert spaces and little LP spaces. Capital LP fail this property. It's amazing because they are uniformly convex, but they fail Opel condition. Very important. You will see why. So we have the following result. Beautiful. That was one of the first one we discovered. Is that if you have Opel condition, if you have a monotone non-expansive mapping, it has a fixed point provided you have what? A comparable element with the image. Okay. So this is almost the first one we discovered. Okay. Then we looked at the case of what happened in the case of let's go back here. I want to show you something very interesting. So how did we get it? We looked at the man iteration. We looked at the man iteration, okay, and we showed by Opel that the weak limit is in fact a fixed point. But wait a minute. The sequence we generate by man here was monotone. So then we ask ourselves, do we have something called monotone weak Opel condition? What does it mean? It means that you have the property of Opel, but for monotone sequences. You see? See this definition here? The sequence yn, we want it to be monotone. Okay? Great. So we call this monotone. I believe here it is. Okay? This definition of monotone weak Opel condition. Okay? Someone will say, okay, so fine. Well, so what is it? What is special about it? What is special about it is that if you look at now capital LP, this is amazing now. Capital LP was this classical Banach space capital P fails the weak Opel condition. That was in the original paper by Opel, and you will see it all the time in many papers that they will tell you capital P fails the Opel condition. But what's amazing is it satisfies the monotone weak Opel condition. That was a surprise to us. Now we go. Okay, so we have this beautiful theorem when you add in the so now we wanted to know what happened if we go to uniformly convex, like Browder and Good. The Opel was first. It's really funny. These are the ones that we did first. And then we asked, okay, so what happened to uniformly convex Banach spaces? And here it is. We do have a fixed point. In other words, we do have the analog of Browder and Good in the case of uniformly convex. Next. Okay? What about monotone? Asymptotically non-expansive. By the way, I did not even touch monotone uniformly Lipschitzian mappings. We started with monotone asymptotically non-expansive mapping, okay? And we really struggled. But then, of course, we proved it. We proved that this is the definition, of course, of what is monotone asymptotic non-expansive, as you can guess. And now we have this beautiful what? Theorem. It's fairly recent, by the way, that if you have Banach space, which is uniformly convex, okay, and you have a monotone asymptotically non-expansive mapping, I assume it is continuous, then you have a fixed point, okay? Then you have fixed point, provided always that there is that x0 comparable to t of x0. If you don't have that, there is no fixed point at all, because tx equal x a fixed point, then you have that assumption. If you don't have it, forget about fixed point, okay? Great. Now, before I let you go, what happened to shoe? Okay, so we have the Browder and Good, and now we want to look at what? The approximation. So what happened? Great. So for that, let's go back to the iteration by shoe. So this is very important. Okay, that's why I rushed it a little bit, because I want to bring you to these ideas. Okay, so Shu, how did he do it? What was the originality of Shu? Okay, his originality is that here, this power, okay, it was not in the original definition of Krasnodębski, Mann, and Ishikawa. None. Okay, but he introduced that. Why? Because he wanted to capture the fact that T is almost non-expansive. So it's the iterates when you go to infinity that you are almost non-expansive. Okay, so fine. Let's take x0, which is comparable to t of x0, and look at this iteration by Shu. Okay, the modified man. Okay, this one here. Okay, we were not, till today, we are not able to prove that this sequence is monotone. Keep in mind, someone will say, okay, so why do you need monotonicity of the sequence? Because remember, if you look at Opel condition, you have the weak Opel condition and you have the monotone weak Opel condition. If you stay with weak Opel condition, okay, then you have a problem with what? With capital LP. It doesn't satisfy this property. But if you restrict yourself to monotone sequences, they have some amazing properties. For example, monotone sequences in a reflexive space, they converge weakly. That's not the case for any sequence. So it has a lot of nice properties, okay, that we are not able. So what we're able to do, we're not able to prove this, okay, at all, but this is what we did. What happened is, if you replace n by the Fibonacci sequence, okay, if you replace n by f of n, okay, which is the sequence given by the Fibonacci sequence here, okay, as defined above there, then we are able to prove what? That this sequence or iteration, okay, we called it Fibonacci man iteration, it is monotone. So now the question becomes, do we have similar result as Shu? And here we are. So the first one, okay, is here is the first one, okay, which is similar to theorem 2.2. There are two theorems by Shu. Huh? One, you have some kind of compactness. The other one, you have weak convergence. Okay, there are two of them. Okay, one strong convergence and one weak convergence, and that is even the title of what? Of the paper by Shu. Okay, so this one captures the strong convergence when you assume that one of the iterates is compact. Okay, so if you assume that one of the iterates of T is compact under the same assumptions, but be careful, you are using the Fibonacci man iteration. You are not using Shu's iteration. Okay, and the next one, okay, is the theorem 2.1, which is the weak convergence. Okay, where you have what? In this case, you are using. By the way, in the paper by Shu, he uses weak Opel condition, and here I am assuming what? That the norm is monotone. Okay, and a norm monotone. What we found a class of Banach spaces partially ordered that satisfies the monotone. If the norm is monotone, it satisfies the monotone Opel condition, and here is the condition, what it means by monotone. Okay? Now, let me say, before I let you go, because I'm almost done, let me give you two books, okay? Here is one, okay, by Siegfried Karl. Karl is the editor-in-chief of Nonlinear Analysis, and Seppo Heikkilä. Heikkilä is retired, okay? He's a Norwegian mathematician, and he's retired. I wrote to him once, and he wrote back saying that he's now, he stopped doing any research. But he wrote two books, okay? And he did work, you will see the second one is very interesting. But this one, it was supposed to be, let me show you the previous one, the older one. This is the older one, okay? The older one was written, Heikkilä wrote it with Lakshmikantam, okay? And look at the title, it's amazing. Monotone Iterative Techniques for Discontinuous Nonlinear Differential Equations. Beautiful book, truly beautiful. Okay, so this book that you see here originally was planned to be written by the three authors, Carl, Hekila, and Luck. But Luck passed away, and finally Carl and Hekila wrote the book, and they dedicate the book to Lakshmikantam. Look at the title now. Again, is fixed point theory in ordered set and applications to what? Differential integral equations to game theory. It's beautiful. So it shows you this monotone mappings. They have major applications. Okay, and finally here are some of the papers that were published recently, and I inspired from them. It's very condensed what I gave you. I apologize for that, but I wanted to give you an overview. In other words, just an overview. There are so many questions that are still open, and I hope that this will give you just some kind of flavor of what kind of problems we want to work in. And again, I would hate to see, because there's so many beautiful open problems in terms of classical mappings. I did not talk about, of course, how to extend this as Jashimsky did and Mondor-Friedan did, how to extend the partial order to graphs, okay, or what we call now weighted graphs. Beautiful stuff there. I couldn't do that. And finally, I knew I'm not going to be able to do it, which is recently me and Abdurrahim Khan, we looked at the case of multi-valued as well, okay? I hope that you did enjoy this. It was a little bit intense. I apologize for this. And if you have any question or if you want to ask anything, I'll be more than happy to entertain any question you have.